Hello students, today we'll learn the topic design of shear reinforcement in beams. After the design of beam for flexure, the second part is design of shear reinforcement and that is also equally important. Let's try to understand what is the mechanism of the shear transfer in beams. Since the strength of concrete in tension is considerably lower than strength in compression, design for shear is of major importance in concrete structures. The behavior of RCC beams at failure in shear is distinctly different from their behavior in flexure. In shear, beam fail suddenly without sufficient advance warning, and the diagonal shear cracks are considerably wider than flexural cracks. Let's try to understand this mechanism with these two diagrams. Now, this explains us the shear strength of beam without shear reinforcement. So this is exterior beam column joint. It's a simply supported end with the longitudinal tension bars at bottom. At failure, the shear crack originates from this corner and it proceeds at an angle of 45 degrees towards the quarter span, which divides this beam into two parts, part 1 and part 2. Now, along this crack, which forces act? So actually, we'll try to understand what is the shear resisting capacity and how can we calculate. So here, shear resisting capacity is formed by three components. One is VD, and that is shear resisted by dowel action of flexural reinforcement. It is nothing but the force induced to prevent the slipping of bars from surrounding concrete. So here is the arrow VD, and that is the tension in the steel and dowel action which exists here. The second part is VA, and VA is along this the crack. So it is the interface shear transfer due to aggregate interlocking. So aggregate interlocking provides this component of force. And the third one is this VC. What is this VC? It is the shear resisted by uncracked concrete in compression zone. So this is how all these three components work. Now, how the mechanism commences here. So the mechanism of shear failure commences with dowel action reaching its capacity first. So crack starts from this point once the dowel action exhausts. Then the second component is the aggregate interlocking, and after the failure of first two components, large shear force is transferred in the concrete of this compression zone, and which leads to sudden and explosive failure. Well, so when this shear acting on the section is greater than the shear capacity of the concrete, the diagonal crack emerges. We saw this. And in order to prevent the formation of diagonal cracking and its widening, additional shear resistance in addition to the earlier three components, that is VC, VA and VD, we need additional resistance, and that is which is required to hold together the two parts of the beam, and which are on these are the two parts which are on the opposite side of the possible cracks. The additional shear resistance is provided by the transverse reinforcement, and which is called as shear reinforcement. So today we will see how can we provide this shear reinforcement. So shear reinforcements can be provided by using these three formats. One is vertical stirrups, which are at right angle to the longitudinal reinforcement. Second, inclined stirrups making an angle 45 degrees or more with the longitudinal reinforcement. Third, inclined bent up bars at an angle of 45 degrees or more. And fourth one, combination of first or two along with three. Now the practice of providing inclining stirrup is not there in the field, since there are a lot of complications in working with these inclined stirrups, but vertical stirrups is a very common practice. Let's see now what IS code prescribes about minimum shear reinforcement. So as per clause 26.5.1.6, the minimum shear reinforcement in the form of stirrup shall be provided such that, so this is the equation given by IS code. It is ASV divided by B into SV shall be greater than or equal to 0.4 divided by 0.87 into F1. Now let's try to understand different terms in this equation. So what is ASV? ASV is the total cross-sectional area of stirrup legs effective in shear. Now here we have or 3 leg stirrup or 4 leg stirrup. So let me show you some diagrams here. So if we are providing such one ring
with this hook at the top. So 1 and 2. So this is 2-leg stirrup. Then if you want to understand what is 3-leg stirrup, so along with this master ring, one additional hook is provided, and that is called as 3-leg stirrup, 1, 2 and 3. 4-leg stirrups, so 2 rings are provided. One is, this is the master ring, and this is the secondary ring. This is called as 4-leg stirrup. The 4-leg stirrup also can be provided in this fashion. So this is one ring and this is the second ring. So this is also 4-leg stirrup. So any element you can provide. All these are 4-leg stirrups. So this total cross-sectional area of the stirrup legs, that means if this diameter is 6 mm diameter, so pi by 4 into 6 square gives you area of 1 leg. Such type of multiplied by 2, so it's a 2-leg. If it is 3-legged, then multiply by 3. So likewise you can calculate the area of total cross sectional area, ASV. SV is the spacing of the stirrups. B is the width of wave in case of T beam, or is the width of the beam in case of rectangular beam. Fy is the characteristic strength of stirrup. Well, while designing we can use FE 415 or 500, but while designing shear reinforcement, IS code restrict the grade to 415 Nm per mm square only. Well, whatever this provision of minimum shear reinforcement is given, this need not be complied with, where the maximum shear stress calculated at that section is less than half the permissible value. It means VU. What is this VU? So VU is the actual shear force at that section, and if that value is less than 0.5 VUC, so VUC is the capacity of that section, then in this case it is not necessary to provide minimum shear reinforcement, so we can provide nominal shear reinforcement. And such zones are present normally at near midspan, where the shear force is quite less. And the second point is the members of minor importance, for example lintels. Well, reasons for providing minimum shear reinforcement. So the first one is to prevent sudden shear failure. Second one is to impart ductility to give warning of impending failure. Third one, to confine the concrete and increase its strength and rotation capacity. Fourth one, to prevent premature failure if the concrete cover bursts away and the bond to the main reinforcement is lost. Fifth, to act as ties for holding the longitudinal bars in position while concreting, so as to maintain clear cover and clear distances between the bars. And the last one, it maintains dowel capacity by preventing the downward movement of longitudinal bars. Well, there is one more clause given by IS code. It is for maximum spacing of shear reinforcement. And what is that clause? It is the spacing should not be more than 0.75 D or 300 mm, where D is the effective depth, whichever is less. And for inclined stirrups, it is only D or 300, whichever is less. Now, if you provide this spacing by providing this clause, that reinforcement is called as nominal shear reinforcement. So, when the portion of the beam where ultimate shear to be resisted is less than half the ultimate shear capacity of RC section, that is VU divided by 0.5 VUC, then it is necessary to provide nominal shear reinforcement. Now in this nominal shear reinforcement, we can provide a minimum bar diameter and maximum permissible spacing given by these two equations. Well, now let's see design of shear reinforcement. So there are number of steps A, B, C, D, E, F, G. One by one we will see this, and there are a lot of notations which you have to remember here. So the first step is determination of maximum ultimate shear at support, and the notation is V suffix U max. So we call it as VU max. So for simply supported beam of span L carrying UDL and intensity WU, VU max is given by WU into L by 2. So it's simply that we are finding the reaction at the support. But in case of continuous beam, the final reaction at support by considering the effect of fixed end moment is to be considered as VU max. So in continuous beam we consider moment distribution method, and in moment distribution method we calculate the reactions due to external loading, then reactions due to fixed end moments, and we add or subtract according to the directions of the reactions, and finally we get the reaction at that support, and that reaction is nothing but VU max. So second step is determination of ultimate design shear.
The notation is V suffix U D at critical section. So we are finding ultimate shear design at critical section. Now the question is, what is this critical section? So let's try to understand how to get critical section. So two different cases are mentioned here. So in the first case, at the supports which offers compression reaction, the diagonal crack starts from the face of support and runs upwards at approximately 45 degrees toward the span of the beam. So in this case, the critical section is considered at distance d from the face of support, and the second case is at the supports which offers tensile reaction. The diagonal crack starts from the face of support and runs backwards. This is important. Runs backwards at 45 degrees in the support region. So here crack moves towards the span, and here crack moves inside the support. So obviously critical section is considered at the face of support. So let's try to understand this with the help of these two diagrams. So this is the exterior beam column joint, and this is the incline crack. So it starts from this corner and proceeds at an angle 45 degrees. So this angle is 45, hence this height of the beam is equal to this distance, and hence critical section is at distance d. If it is the support of continuous beam, so on left side also beam, on right side also beam, so in that case also you have to consider the critical section at distance d for both the sides. Yes, this is the case 1. Now case 2. If the column supports a cantilever beam, then obviously the crack which starts from here and it just proceeds somewhere in the support at an angle 45 degree, and hence critical section is to be considered at an angle, at the face of the support. The second case is when the secondary beam transfers load to the main beam and their top are at one level. So the force which get transferred is in the lower portion of the main beam. So obviously tension reaction get generated in the upper portion, and hence the shear crack starts and it proceeds inside the, so crack starts from here and it proceeds inside the section, and hence here also the critical section is considered at the face of the main beam. So these are the two cases for considering the critical section. Now let's consider this diagram where the critical section is considered at distance d, and we'll try to calculate VUD. So that is the ultimate shear force at critical section. So it is nothing but VU max. So what is VU max? VU max is the support at the center line of the column minus WU, which is UDL, into distance. What is that distance? Distance is this total distance. Okay. So this is BS by 2, where BS is the width of this column and BS by 2 is the half the width plus distance D. So we are just subtracting that this force minus the reaction and we get this VUD. So this is for supports offering compressive reaction. And for the second case, when support offers tensile reaction, when the critical section is exactly at the face, then simply it is VUD is nothing but VU max. Well, the next step C is determination of allowable ultimate shear VUC max. So it is necessary to check that VUD must be less than or equal to VU max, otherwise it is necessary to increase the section. Now how do you get this VU max? So VU max is nothing but tau UC max into BD, and tau UC max, the values are given in IS code on page number 73, table number 20. So in this table you will find as grade of concrete increases, the value of tau UC max also increases. The values are given in Newton per mm square. Well, and if the check is not satisfied, then you have to increase the section. Then next step is calculate ultimate shear resisted by concrete section. So we are calculating the capacity of concrete section with only longitudinal reinforcement. And how do you find this capacity? So it is VUC is equal to tau UC BD. See, remember, this is tau UC max and this is tau UC. So tau UC max we have to refer table number 20, and for tau UC we have to refer table number 19. Now this tau UC is the shear stress corresponding to the percentage of the steel. So in the next slide, this table is given, which is given in IS 456 on page number 73. So if you study this table, you will observe different grade of concretes are given. So starting from M15 to M40 and above. As the concrete grade increases, the value of tau C also increases. See, here it is 0.28, 0.28, 0.29, 0.29, 0.29 and 0.3. In the first column, the percentage of steel is given. So the percentage of steel we can calculate here. This is the equation which is given here, 100 into AS divided by BD. AS means area of tension steel, and BD means cross sectional area, B is the width of the wave, and D is the effective depth, and multiply by 100 since we want percentage. Well, as the percentage of steel increases, the value of tau c also increases. See, for each column you will find the values are increasing. Okay. Now, once you get this value of tau uc, substitute in the earlier equation and get the value of VUC. Next, E, calculate the ultimate shear resisted by minimum vertical stirrups. And one more notation you have to remember here, VUSV minimum. So, VUSV minimum is equal to 0.4 BD. Well, once you calculate VUSV minimum, then in the next step, we'll calculate the ultimate shear resistance of the RC section with minimum stirrups. It means what? We have to add VUC plus VUSV minimum. So, it is the capacity of concrete section with longitudinal reinforcement, and this is capacity of minimum shear reinforcement to resist shear. Now, we have to check if VUD is less than or equal to VUR minimum, then provide minimum shear reinforcement. So, this design is given in the step number H. But if VUD is greater than VUR minimum, then provide design shear reinforcement. Okay. Well, so only in this case, if VUD is greater, then you have to provide design shear reinforcement. Okay. So first we will calculate how to design this shear reinforcement. So you have to calculate now VUS. What is this VUS? VUS is the shear to be carried by shear reinforcement. So it is nothing but VUD minus VUC minus VUSB. Now this VUSB is new term here. What is this VUSB? So VUSB is the ultimate shear carried by bent up bars. So according to IS 456, that capacity you can calculate by using this equation. So it is 0.87 Fy into ASB into sin alpha. Well, what is ASB? It is the area of bent up bars, cross sectional area of bent up bars. If two bent up bars are provided, then that is the cross sectional area of two bent up bars. And what is sin alpha? So it is alpha is the angle with which the bent up bars are provided, and normally it is 45 degrees. Well, but if bent up bars are not provided, then VSB is 0, because nowadays the practice of providing bent up bars is discontinued, and we just provide curtail bars and extra top bars. So if bent up bars are not provided, then simply consider the VSB 0. So this equation will become VUS is equal to VUD minus VUC. That's it. Once you calculate VUS, then we can calculate spacing and zoning of shear reinforcement. Well, now the beam is divided into three zones: zone 1, zone 2 and zone 3. Let's try to understand each zone. Well, so zone 1, it is called as zone of design shear reinforcement. So we have calculated VUS value, and that VUS value we can substitute in this equation. So what is that equation? So spacing, SV means spacing of shear reinforcement, is equal to 0.87 Fy into ASV into D. We saw the ASV means it is the area of the shear reinforcement, and D is the effective depth. And VUS, already we saw, we can calculate this VUS by subtracting VUC from VUD. Well, but again this spacing we have to check against the maximum spacing, and that shall not be more than 0.75 D or 300 mm, whichever is smaller. Well, up to what distance we have to provide this zone 1? So this is the equation. LS1 is equal to VU max minus VUR minimum divided by WU. Now this is zone 1. Zone 2, so it is the zone of minimum shear reinforcement. Now that spacing is given by 0.87 Fy into ASV divided by 0.4 B. Well, again this spacing also you have to check against the maximum spacing, that shall not be greater than 0.75 D or 300 mm, whichever is smaller. Up to what distance you have to provide this LS2? So it is VUR minimum minus 0.5 VUC divided by WU, or simply you can calculate VU max divided by WU minus LS1 minus LS3. So this is zone 2. In zone 3, this is the zone of nominal shear reinforcement, and the maximum spacing which is allowed that we can provide here, and that is 0.75 D or 300 mm, and the remaining part is LS3, that is 0.5 VUC divided by WU is the zone 3 part. Now we will try to understand this with the help of this diagram. Well, so this is the beam, and I had taken this YY section. This is the section at which the shear force is 0. So the entire beam is divided into two parts. This is the left side and that is the right side. Okay, so this is the shear force diagram of the left hand side part. Okay, so VU max is the reaction and there is the maximum shear force here. Okay, since the critical section is considered at distance D, so VUD is the shear force at that critical section. Okay, now this VUR minimum is made up of two parts, already we saw, and that is VUC and VUSV minimum. So VUC is the capacity of concrete section and VUSV is the shear resisted by minimum stirrups. Okay. Now LS1 is the zone which starts from VU max and it is up to VR minimum. Okay, so that's why we have written that equation VU max minus VR minimum divided by this W, that gives you this distance LS1. Okay, and the spacing, this is the equation of the spacing, already we saw this. Okay, now after when LS1 ends, LS2 starts. So the LS2 is the zone of minimum shear reinforcement. So it is the zone which starts at VR minimum and ends at VUC by 2, and hence that second equation we have written as VR minimum minus VUC by 2 divided by W, that gives you this LS2 distance. Okay, and LS3, well, it is VUC by 2 divided by W, that gives you this LS3. Well, for this spacing as well as for this spacing, one check we have to satisfy, that is 0.75D or 300 mm, and the maximum spacing we can provide in the zone 3. Please remember the equations which I have given you for LS1, LS2 and LS3, it is only when the beam is subjected to UDL. If any point load is acting in between somewhere here, then obviously you have to consider that effect of that point load into consideration, and accordingly you have to rewrite the equations of LS1, LS2 and LS3. That also totally depends on the where is the position of the point load. Well, now when all these three zone exist, this diagram is there. Okay, but as we saw that when VUD is less than VR minimum, then design shear reinforcement is not necessary, then only minimum shear reinforcement is sufficient. So in that case zone 1 is absent, so obviously LS1 is equal to 0. So for zone 2 there is a little bit variation in the equation of LS2. This equation is same, so it is VU max minus 0.5 VUC by W. So instead of VR minimum we are writing here directly here in VU max. That means LS1 merges into LS2 and total is that LS2. Well, and zone 3 is same as that of the previous case, it is zone of nominal shear reinforcement. Okay, so accordingly we can provide all the 3 zones from the left side, similarly 3 zones for the right side, and this completes the design of shear reinforcement. Yes, thank you students.